Hello and welcome to our first lecture on the quantum field theory. So in this lecture, we are going to address a very important question, which is why do we need quantum field theory? Now, quantum field theory is the basic mathematical language that is used to describe and analyze the physics of elementary particles. It is one of the most successful scientific theory of all time, predicting the experimental results with ultimate accuracy. It is a theoretical framework that combines four important branches of physics: the classical field theory, which is given by the CFT. Second is the special theory of relativity, and the third is none other than our quantum mechanics. So let me take you through a brief historical journey of quantum mechanics. It all began with Max Planck's bold postulate that energy could be quantized, represented as discrete particles with energy E. It is given by this particular formula: E is equal to h cross omega. This idea was the cornerstone that resolved the blackbody radiation puzzle without encountering the dreaded infinities. Now, the implications of this quantum leap were further illuminated by none other than our Albert Einstein, who explained the photoelectric's frequency dependency, reinforcing the particle nature of light. Now, following this revelation, a cascade of innovative thoughts emerged from the greatest minds of 21st century: Bohr, Dirac, Born, Schrödinger, and Heisenberg. They extended the concept of quantization to particles, achieving a remarkable success in describing the subatomic world. Dirac, in fact, particularly formulated a relativistic theory of the electron that resonated deeply with the experimental findings. Yes, despite this success, quantum mechanics of particles revealed the philosophical and practical implications. Now, these philosophical and practical implications are going to serve as our motivation for us to study the quantum field theory. Let's start with the motivation. The first is the missing link. Now, the quantum mechanics introduced us to photons, but traditionally, light was described as electromagnetic field. Now, this discrepancy begged the question: how do we quantize fields? The missing link, this missing link between the particle and the field description is what quantum field theory aims to address, as we'll explore the framework for quantizing fields. Not only we are going to encapsulate the photons, but all the elementary particles, offering a unified language for us to study the quantum realm. Now, the second challenge is the relativistic challenge. So, in particle quantum mechanics, see, the particle quantum mechanics is valid only in the non-relativistic regime. It's also called as the non-relativistic quantum mechanics. Now, the thing is, why it is valid in non-relativistic regime is it is not just because it uses the non-relativistic Hamiltonian. What do I mean by that is we know this from quantum mechanics, h cap e psi. So, but the thing is, it's not just because it uses this non-relativistic Hamiltonian, but it uses the concept of potential. What do I mean? Is let me rewrite this in a more detailed way. H hat is minus h bar square upon 2m square plus b of x. It's because it uses this concept of potential. So you might ask, what is the problem? What is the problem here in using the potential? The thing is, this is invalid in any relativistic theory, as it assumes, as this particular term assumes, the transfer of information at infinite speed. Again, you might ask, what's wrong in that? The thing is, nature has a limit, that is the speed of light in vacuum. So, this is invalid in any relativistic theory. The non-relativistic theory, quantum mechanics, by its very nature, it defies the principles of relativity. It implies that the potential imply the instantaneous transfer, information transfer, and impossibility in any relativistic theory. Now, furthermore, the third question, the third motivation is injustice with time. What do I mean by that is in non-relativistic quantum mechanics, we know that the x is treated as an operator, right? We denote it by the cap, which represents the operator in quantum mechanics, in normal particle quantum mechanics, in non-relativistic quantum mechanics. But t, if you see, is treated as a mere parameter. You, what do I mean by that is the x and t are treated at different footing. This is where the quantum field theory steps in, merging the space and time in a coherent in QFT in a coherent space-time continuum, respecting the symmetries of relativity. Now, the fourth one is the practical dilemma. So in nature, in the natural world, in our real world, particles are not eternal. They can be created and destroyed. Consider the well-known example of the beta decay itself, where a neutron transforms into a proton and an electron and an antineutrino. The traditional quantum mechanics focused on stable particles falls short in explaining such processes. This is where quantum field theory again steps in. In quantum field theory, however, it embraces the creation and the annihilation of particles, enabling the precise calculation that aligns with the experimental evidence that can be found in our everyday life. So, what I'm so this four serves as the very basic motivation to study the quantum field theory. So quantum field theory is not just an extension of quantum mechanics. You need to realize it. It is a necessary evolution for us to address the practical and the relativistic challenge that arise in the quantum world. So if you want to study more about this, more about the need for QFT, Peskin and Schroeder has an excellent I think 4 or 5 pages on it. I'll just link the book in the description. You can check out the link that will lead you to the Amazon site, the book. So yeah, so let's end this video here. In the next video, we'll study the I think we are going to study the creation and the annihilation operator. Why do we need, like, it's just a basic recapitulation of quantum mechanics. So that will serve, that's going to serve as a very important for us. So, yeah, thank you so much.